Welcome to the 12th and final lecture on approximation algorithms. Today we will talk about the Steiner forest problem, and we will attempt to solve it via the Primal-Dual approach. So let's start with defining the problem. In Steiner forest we are given a graph with edge costs. And also we have a set of k pairs of vertices S1T1 up to SK like here. So we have one pair S1T1, one pair S2T2, and one pair S3T3. And what we want to find is an edge set with minimum total cost, such that in the subgraph that's spanned by the edges, all of these pairs are connected. So in this case, this would be the solution. We have one subgraph where S3 and T3 are connected, and we have one connected subgraph where S1 and T1 and S2 and T2 are connected. And if you look at this smaller graph here, this has total cost 7. It connects both pairs. If we connect them directly, S1, T1 here and S2, T2 here, that would cost us 8. So this is cheaper going via these vertices that are not in the pairs. This is a quite general problem, and it generalizes many problems that you already know. For example, as a special case, we can define the shortest path problem. The shortest path is just you have one pair of vertices, S and T, and you want to find the shortest path between them, so the smallest edge set such that they are connected. Also, it generalizes the minimum spanning tree. If we just take every edge as a pair, then we want that all the vertices that are connected somehow still are connected in the spanning tree. And then the cheapest one, that gives us the minimum spanning tree. And we can also generalize the Steiner tree problem. There we only have one set of terminals and they all have to be connected. So if we take every pair of them and put them into our set R, that gives us exactly the Steiner tree problem. Do you have some ideas how to solve this problem? It doesn't have to be very good, but just how we get some solution. I briefly want to discuss two approaches that people usually choose first. The first one is we just compute a shortest path between all of these pairs of terminals and we merge them. And the second one is we compute a Steiner tree on the set of the terminals. Remember, those two things were special cases we have here, so we can try to solve this via their special case. The problem is both of these approaches perform poorly. Can you find an example for each of these approaches where the solution is quite bad? Let's first have a look at an example for the first one, merge k shortest SITI paths. So I take a graph that has k pairs, and between each of them we have a direct edge of length 1. Now I add two more vertices. One I connect to all the S vertices, one to all the T vertices, and the cost is epsilon, so it's very, very low. And then I connect them via an edge that costs 1. Now the shortest path between each pair is clearly the direct edge, which costs just 1. But the best solution for our Steiner forest problem connects everybody to these two vertices and the green edge. And then the total cost for the shortest paths is k, and the total cost for the optimum solution is 1 plus 2k epsilon. So as long as the epsilon is small, this is very close to 1, and then the ratio is k to 1, so this is very bad. For the second, it can be even worse. If you just look at this very small example here, we have two pairs, a direct edge between them that costs 1, but we want to find a Steiner tree on the set of terminals, so we try to find a tree that connects all of them, not just add one more edge that has very, very high cost. And now the Steiner tree we find here has all the edges, but clearly the optimum solution is just these two directed edges. So here you can get an arbitrarily bad ratio. Now these two approaches, they are not very good. But if we look at this here, I mean, there's no reason why we should have this edge. So why do we put it in the solution? We could take the solution of the Steiner tree and just throw it out because we don't need it. So the difficulty for us is we have to find out which of the terminals belong to the same tree of the forest that we want to obtain.